When a robot climbs a ladder on camera, your first instinct might be to assume it is just fancy pre-programmed movement or even computer-generated imagery. That skepticism is healthy because for decades, real-time physical autonomy has been impossible due to the time lag between thinking and acting. The Figure F.03 demo changes that narrative entirely by proving we have finally crossed a threshold where end-to-end learning solves the latency bottleneck. This shift moves our engineering constraint from raw compute power to model architecture efficiency, turning agentic AI into a functional reality rather than marketing fluff. The viral clip of the robot climbing is not just about dexterous fingers or complex limbs. It represents a fundamental breakthrough in how robots perceive and interact with their environment. Historically, robotics failed at complex physical tasks because the traditional loop of perceiving data, planning a solution, and then executing an action introduced too much latency for real-world physics to tolerate. If you have ever tried to control a robot remotely or run heavy algorithms on older hardware, you know that even a fraction of a second delay can cause a system to crash or fail catastrophically when dealing with moving parts. The F.03 system bypasses this entirely by utilizing end-to-end learning, where perception and action are processed simultaneously rather than through intermediate planning steps that create drag in the pipeline. This architectural shift means we are no longer limited solely by how fast our chips can compute numbers. Instead, the primary bottleneck has become how efficiently our model architecture processes visual data to drive physical motion at once. In previous generations of robotics, teams often had to rely on massive cloud round trips where a robot would send video footage up for processing and wait seconds for instructions back down. That approach simply does not work when you are climbing a ladder or manipulating fragile objects that require instantaneous reaction times. The F.03 demo proves the AI thinks as fast as it moves, eliminating the lag that made physical autonomy feel like science fiction for decades. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand why this is now possible at scale, we have to look beyond just the software and examine the hardware enablers that make research affordable enough to iterate on these models rapidly. A major barrier has always been cost, because training end-to-end learning systems requires massive amounts of data collection from real-world trials. The Figure F.03 leverages a specific innovation called the LELEP hand, an anthropomorphic dexterous hand designed specifically for this kind of scalable learning. This component costs approximately $2,000 USD to assemble, which is roughly one-eighth the cost of competitors like the Allegro hand that can often exceed $16,000 in price tags. This democratization of hardware means engineers are no longer locked out by budgets that required millions of dollars just for a single robotic hand. The Leap hand allows teams to build functional units from standard parts in about 4 hours, making it feasible to deploy dozens or hundreds of robots simultaneously to gather the diverse training data needed for robust AI models. Unlike expensive proprietary units that might fail under high torque output over long durations, this solution offers comparable performance while maintaining durability during extended manipulation tasks. The result is a feedback loop where better hardware enables more data collection, which in turn trains smarter architectures capable of handling complex physical constraints without breaking the bank. When we connect these dots, we see that the F.03 demo represents a closed-loop system where perception, hypothesis testing, and action happen continuously without human intervention or external dependencies. This is not just about executing a script. It is about running an internal loop where the robot constantly asks itself questions like whether a ladder rung is stable before committing its weight to it. In this context, we are seeing the digitization of innovation cycles similar to frameworks used in advanced engineering platforms that consume information and test hypotheses without manual debugging steps required by traditional CAD or simulation workflows. The robot does not need a human operator to verify every step because the model architecture has learned to handle the uncertainty of physical interactions autonomously. For practitioners watching this evolution, your judgment on what projects are viable now versus those stuck in simulation hell needs to shift accordingly. You can no longer assume that simply throwing more GPU power at a problem will solve it. Brute force compute is no longer the silver bullet for every engineering challenge. The era where raw processing speed was the only metric of success has ended, and the new frontier is architectural efficiency and end-to-end learning pipelines that minimize latency to near zero. As an engineer or data scientist, you must now prioritize designing systems where software agents can coordinate complex physical tasks through low-latency inference rather than just focusing on model size alone. This realization changes how we approach career development in the AI era. Understanding this shift helps you judge which projects have a path to real-world deployment and which are merely theoretical exercises that cannot handle the messiness of the physical world. It signals a move toward systems design, where the constraint is not whether your chip can run fast enough, but whether your model architecture can process perception and action simultaneously without intermediate processing steps creating delays. The question for every team building agentic AI now becomes one of architectural efficiency rather than just raw computing capability. The primary engineering constraint has shifted from raw compute power to model architecture efficiency, and this demo proves we have crossed the line where thinking is fast enough to touch reality. Previous attempts failed because AI reasoning was too slow. F.03 shows us that perception and action can happen in unison without lag. End-to-end learning is not just a buzzword here. It is the specific mechanism that eliminates latency, validating that software agents can now physically interact with the world in real time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.